Liam's going to explain question 10, the question, and then sort of how he did it, and also the investigation, okay?
Suppose that a number of 5 by 7 rectangles are placed on a large grid of unit squares,
He's actually like
so that each
25 years
rectangle
old.
covers exactly 35 of the unit squares. The rectangles can be placed either horizontally or vertically, and they may overlap. Find the largest integer n for which it is not possible to cover exactly n unit squares in this way.
Wait, what does that mean? Rectangles can be placed either horizontally or vertically, and they may overlap.
Yes.
Each rectangle covers exactly 35 little squares. Find the largest integer n for which it is not possible to cover exactly n unit squares in this way. What does that even mean? So wait, so like for example, like 3 is a number you can't cover exactly. Is that right?
Yes.
Yes. Anything below 35 you can't cover exactly.
Okay.
But you can find the largest.
So the answer is greater than 33.
30. No, the 30. It's greater than 35.
Alright, so first, I will show you can get anything greater than or equal to 45. To get 45, what we can do, so we have a rectangle, right? 5 by 7. It's looking like a rectangle, guys. So how can we add 5 to this? Exactly 5 unit squares. How can we add it?
Make it 5 by 8.
Exactly, Sebastian. We can place this and do add 5. We've added 5.
That's what I said.
We can keep repeating this process to get.
How do you add 5? Don't you add 10 at least?
No, because you have 5, 7. We move it 1 up. 1, 2, 3, 4, 5.
So you're allowed to use as many of rectangles as you want.
Yeah, first I'm showing that you can get 45 first. I'm showing you can add 5 once you have your original rect. So then that means we can get 45. Now for 46. 46. We place our rectangles like this. One, 1, 1, 1. Alright. Now we're looking at 46. Alright?
You could deduct a 4 by 6 square. A 4 by 6 rectangle. Because, like, if you have 2 rectangles, right, that add up to 70, but a portion of it overlaps, then you have to deduct that portion from 70.
Yeah, sure.
So in this case, 70 minus 46 is 24.
That's the idea. So what we're doing, we're overlapping them so it goes 1 across and 1 down from the other.
How do you make 47?
So this has 11 more squares, so we get 46. Now, how do we get 47? Well, this is how we can get 47. We fill the corner. Like this. You see, we filled 1 corner.
That was disappointing.
47. Now, any guesses as to how we get 48?
You just fill another corner.
Sebastian's on the money there. Now we've got 48. What a victory. Now, 49. How can we get 49? Think about 7 and 5.
Exactly. You have to overlap 2 5 by 7 rectangles such that you have to deduct a 3 by 7 rectangle from it.
So just do the same thing the other way.
Yeah.
Yeah. How would we say how many did how put it work, putting the hours and people hours?
Alright, now 50. How do we get 50? Let's take a look. What happens if we go like this?
But we already had 50.
No, we don't. Oh, we do, but we're going to get it another way.
Just
So
deduct the 5 by
we get 50 another way because it advantages us. 2, 1. 2, 1. How many are here?
Not many.
Let's count. We added 5. Oh, no, we added 4 because we removed this one. I was right. We removed that one, so we added 4. Now, this gets us 50.
How do you prove?
Alright, so now how can we get 51? What happens if we fill this corner? What do we have now? 51.
52.
Now, how many values do we have here? Let's count for everyone to see. 1, 1, 2, 3, 4, 5, 6, 7. Why is this significant? We can add 7. All of those constructions, we had a face of length 7 exposed, untouched, unused. So, do you see what we can do? Given we have exposed faces of a length 7, which are straight, we can place an offsetted rectangle like this, plus 7. And we can repeat that process.
Possible.
Because of that, we can get everything above 45.
So why doesn't this work from 35?
Because we can't add 1. So now we look at it. Well, important fact of life. When we add a
But how did you find 45? Like, why couldn't you have chosen 40?
You can add without
Yeah.
Was there a
Alright, now we look at, if we make, let's say we start with a rectangle. What we can note, actually, this is general property. We have any rectangle. What is the minimum number of squares we can add? No, so we have any size rectangle, and we can place a 5 by 7. What is the minimum number of squares we can add?
5.
5.
Let's go!
Alright? So now what I will prove is say we place down a 5 by 7. Now let's consider how we place our second piece. We know we cannot keep it a rectangle. Why is this? Let's say we keep it a rectangle. What happens?
What are you trying to do?
I'm showing that 44 is not possible. So I've proven that, right? If it is any size rectangle, we have to add at least 5 for our next rectangle. So say we have. So what happens if? So we have our first 5 by 7. Let's say we place our second, so it's still a rectangle. Why does this cause a problem?
You're saying, like, why can't it end on 2 things that make a rectangle?
Yeah. Or why can't we, our second move, keep it a rectangle if we're going to get 44? If we're going,
Second move.
yeah, like we're considering our second placement. Let's say our second placement kept it a rectangle. So either we add 5 or we add 7, correct?
Yeah.
Plus 5 or plus 7.
Mm-hmm.
However, we know 40 and 42 are not 44, so we need to add another thing. But because it's still a rectangle, we have to add at least 5, so it has to sum to at least 45, which is a contradiction. So therefore it has to not be a rectangle. Let's look at the cases when it's not a rectangle. Now we have a number of ways. We can either have 2 possibilities. Let's first say both of the 2 rectangles we're placing are oriented the same. So the 7 side is parallel to the length 7 side. So then what's the minimal not rectangle shape we can place? So when we add this, right? The minimum that doesn't keep it a rectangle, correct, sir? Rectangle.
11.
It's 11. So first we're supposing that the 7s are oriented the same direction, okay? So this is the minimum. Now let's look at when they're not in the same direction. Alright? When they're not in the same direction, we have this. And then the minimum, right, is this. Plus 10.
So you can either add 11 or 10.
Yeah, but we can't add 9. Which means we cannot attain 44. We shall investigate the investigation. Suppose, instead, we have rectangles of single size 3 by n, for some integer n greater than or equal to 6, placing them on the grid as above, what is the largest integer n for which it is not possible to cover exactly n unit squares? So, basically same problem as 10, but replace 5 by 7 by 3 by n. We break it up into two cases. N is 1 mod 3, n is not 1 mod 3. If n is 1 mod 3, I claim the answer is 4n minus 1. First, I'll prove anything bigger than 4n minus 1 is possible when n is 1 mod 3, when n is 1 mod 3. Because 4 times 2 mod 3 is 2 mod 3, and 2 mod 3 plus 1 is 0 mod 3, so we can also get 4n plus 1. Now we can also get, yeah. Now I need to show we can get 4n plus 2.
We can add 3, like this.
Yeah. 4n plus 1, because it's divisible by 3. Because n is 2 mod 3. Now to get 4n plus 2, what we do is we do the... Let's see. How much is this? Yep. 1, 1. Oh, 3, yeah, 1, 1, 1.
So don't understand your 4n plus 1.
Because n is 2 mod 3. Alright, now we are showing this case. So now we're getting 4n plus 2. You see this is a construction for 4n plus 2?
So this is 3. How much is
this is 3, this is 1, this is 1, so it's like with 2 squares there, n squares here, so it's 4n plus 2.
Okay, so this is 1, 2, 1.
So now we have constructions for...
Wait, so
4n
left-hand
plus 1.
side is 1? Okay.
Yeah, so it's 1. So now I have constructions for 4n minus 1, for 4n, 4n plus 1, and 4n plus 2.
I don't understand. Well, what is this picture? So it's like...
It's like
3
to
by
shift
n
it.
rectangles?
Yeah, but we shift it, we have 1 and then we shift the other 1 across and 1 up.
1 across.
1 up. Yeah, like Gregory is showing.
So how many squares are this?
4n plus 2. Because this is up here, that's n. Yeah.
Oh wait, so n is 2 mod 3.
So then we have 1, 2, and 3 mod 3. So then what we can do in all of these cases, right, we can keep adding 3. So we can get everything greater than 4n.
Okay.
Alright. Now we want to prove we can't get 4n minus 1. Alright. Then we have a bunch of cases. So first, it's called move this. Move this. Alright, so obviously 4n minus 1 is not divisible by 3. Also not attainable by adding like 3's to 3n. Because you need to have at least a 3n by 2n. We cannot attain it with a rectangle. We cannot obtain 4n minus 1 with a rectangle. So we also cannot obtain it with anything where the what's it called? Where the long lengths, the n lengths are parallel, right? Because then we have at least this case, which is at least 4n plus 2. Isn't achievable for 4n minus. So we cannot have them be parallel at all. So now let's suppose they're not parallel. So we have a bunch of cases. Firstly, if it's directly like this, how many do we get? Well, we get 4n minus 9. Alright?
Wait, what? This is it.
Wait,
this
no.
one plus
No, this we get
one.
it way more. We just get a lot.
This one plus
So,
this
what's
one.
it called? This one we get 6n minus 9. Because n is greater than 6. Let's see.
This is 3n.
Because n is greater than 6, 9 is smaller than 2n, right? So then that's bigger than 4n. So then we know we cannot achieve 4n minus.
So
then
this
we know
is
we
like
can't achieve 4n
6n
minus 1.
minus 9.
Saying if it's 0.
That one was 2 mod 3.
Oh, wait, no. Sorry, 2 mod 3. Yeah. When it's 0 or 1 mod n, mod 3, then it's 4n plus 1. Alright, so first I'll show anything bigger than. I'll show 4n plus 2, 4n plus 3, and 4n plus 4 are all achievable. So what we do the same overlapping construction, right? Gets us 4n plus 2. Then what we can do, we can fill in the corners one at a time to get 4n plus 3 and 4n plus 4.
Oh, okay.
Then we
How
can
about-
add 3 to each of those so we can get anything bigger than 4n plus 2 by the mod. Alright, so now what I'll do, alright, now I'm going to erase this. Now we'll show it's not possible for 4n plus 1. Alright, so let's consider first what happens when it's a rectangle. If it's a rectangle, we can only add 3 or n, right? We have to add at least either 3 or n. So what we first know is, suppose it's a rectangle, if it's possible to get 4n plus 1, we know we can't have added an n length edge. So we know it can't be 4 by n, right? Because 4 by n is 1 minus 4n plus 1, so it's not achievable if we have a 4 by n rectangle. So then we have to have it's like 3 by k for some k. But that
Yeah.
3 by k, right? And so we know that it has to be 3 by some k, which achieves 4n plus 1, right? Because we already have 3n at the start, so we can't go adding any lengths of n at some point. So then it has to be 3 by k. It's not possible because 4n plus 1 isn't divisible by 3. Now let's look at non-rectangular. So obviously it can't be parallel for the same reason as before, because we once again get 4n plus 2 when the long lengths are parallel. So now we look at the other case. Once again, we get the same thing. It's bigger than 4n plus 1 because this is 9. Yeah, 4 or 9. And yeah, it was minus 9. So it's 6n minus 9. N is greater than 6. So it's bigger than 4n plus 1.